Hey, good evening. Welcome back to AP Stats Notes Online. I'm going to continue with our two sample intervals and testing. Now we're going to talk about when we want to compare two means as opposed to the proportions for two populations, right? The good news is a lot of what we do is the same as what we've been doing. So I'm just going to make sure that we're again checking both samples for our conditions and things of that nature. And again, our inference procedures are based off of sampling distributions, right? And so no different here. We've got to talk a little bit and think a little bit about what the sampling distribution would look like if we want to compare to sample means, right? So same questions as we've always had. What's the shape, center, and spread of the sampling distribution for X1 bar and X2 bar? And again, remember that we start with the sampling distribution for each of these guys, right, where the center is going to be X1 bar here, X2 bar here, and then normal. As long as the normal condition is upheld, and you have to think about what that meant for means. It's not the same thing as proportions, right? We're not talking about successes and failures. It's all about sample size and what our sample data looks like, right? But then based off of this, they're going to have their own standard deviations. This is, again, terrible notation, just trying to get through this a little bit quickly for you. So we have to think about how we combine everything once we create our new sampling distribution for our differences, okay? So, shape. Well, like before, normal going in means normal coming out. So if our sampling distributions are individually normal, then the combination sampling distribution will also be approximately normal. Sorry, I keep saying normal, but approximately normal. Okay? So when are the sampling distributions for each population or for each statistic, when are they approximately normal, right? Well, like we've done before with our means. That happens when the population distribution is normal or when we sample more than 30 because the central limit theorem kicks in. And I haven't been real picky about this, but it's always nice to sound smarter, right? So if we're going to check our sample sizes, and we're going to check our sample sizes, we're going to do that. And if our sample sizes are bigger than 30, then as you're checking your conditions for your inference procedures, it would be wonderful if you made mention to the central limit theorem applying, okay? So 75 is bigger than 30, central limit theorem applies, suggesting that the sampling distribution is approximately normal. Now, most of that you don't have to say, but just to sort of make mention of the central limit theorem applying would be good, okay? Now, we also talk a little bit about what happens when our sample size is not bigger than 30, right? And so you have to think back to that as well, right? If we have a sample size less than 30, then what we do is we plot that sample data out and see what it looks like. Is the sample data at least not skewed and not have any outliers? And again, it kind of goes back to that weird conversation about how mama looks like the kids and the kids look like mama and all that kind of stuff. But if our sample data is no skewness and no outliers, then our population's probably not going to have any skewness or any outliers. And so it lets us know that the population distributions are going to be approximately normal, so the sampling distributions will be too, right? So you have to think about your sample size all along the way, okay? Now, that's shape. Again, approximately normal going in means approximately normal coming out, all right? Center, well, we're combining two random variables again, right? And when we're comparing anything in mathematics, that suggests subtracting, right? So if I want to find the new center of my sampling distribution for comparing two means, I'm just going to subtract. The two population means, or in most cases, our two sample means. Okay, pretty straightforward. Standard deviation or spread, right? Where does that thing come from? Well, it's a lot like what we did with proportions, where we're combining these two random variables. A little bit of uncertainty in one combined with a little bit of uncertainty in the other means we're going to have more uncertainty. So when we combine these, it's that situation where variances add. So for the combination, we're going to have to add the variances for, let's say, sample 1 and sample 2, right? So now you got to think about what that looks like, okay? And so bear with me with the algebra for just a second, but what that would look like would be standard deviation of the first sample over the square root of the first sample size plus standard deviation of the second sample divided by the second sample size. But that's standard deviation. So now I got to square these to get to the variance, right? Okay, which looks like standard deviation squared over n, right? Plus standard deviation squared over n. But this is variance. These are the variances that are being added. So now I got to square root all of this. Okay? And so we get to our new standard deviation formula for comparing. And it's this, and I'll write it up here actually. So to find our standard deviation, we're going to square roots. Okay? And it's going to be the, and I'm going to do this in terms of sample standard deviation because it really should be. Okay? So it's the sample standard deviation of 1 squared divided by the first sample size, and it's the same thing for the second one. So it does look a little bit different than the standard deviation calculation for a sampling distribution for an individual mean, right? For an individual population, okay? So you have to pay attention to that. Again, third page of your formula packet has 2 tables sitting right there that let you know how to find the standard deviations that you need depending on your situation, okay? And so this is going to be true, obviously, as long as we're not sampling more than 10% of the population, if we're sampling without replacement. If we're doing an experiment, we have to make sure that all the individuals and all the observations are independent of each other, right? And so then we can get to our standard deviation that way, okay? So anyway, a little bit about where that came from. But again, those formulas are going to be in your formula packet, so make sure that you're aware of that. Okay? And then we're ready to start talking about just our inference procedures. Okay? We'll do, obviously, intervals first, and then tests will come in the next set of notes. Okay? So let's go ahead and get into our first inference procedure, right? And we're going to start working towards a confidence interval to try to estimate the true mean difference in our 2 populations, okay? So the first thing we need to talk about a little bit is the formula for standard deviation, or actually for standard error. And remember that standard error is just one of those term differences. That's really about it. We've already discussed just a minute ago standard deviation for our difference. And so as notation goes, you'd look for something like this. Okay. Anyway, it's just the, actually it wouldn't be mu's, it'd be x bars, wouldn't it? X bar 1 minus x bar 2. And it would just be what we talked about before, right? It would be the square root of, and in terms of standard deviation, I didn't write this down, but we probably should real quick, just to show this, it would really be sigma for the first standard deviation over the sample size, plus the square of sigma for the second mean over the second sample size. That's your standard deviation. Standard error, remember, just replaces sigma with the sample standard deviation. And so what we just looked at was your standard error calculation, right? And again, it's just one of those notation things, not a big deal. So that's your standard error. Remember, standard error is part of our margin of error, for our confidence intervals. It's not all of it, but it's part of it, right? And so now we want to get into the formula for a two-sample t-statistic, okay? What is that going to look like? Okay, and we'll do this, and then we'll put it on hold until we get to our test, right? But our two-sample t-statistic, and why are we using t instead of normal? Because we went from using sigma to using the sample standard deviation, just like what we were talking about in our one-sample stuff. So what does that look like in our two-sample stuff? So we're going to have to get into a t-distribution again. Our two-sample t-statistic would look like, right, we have to have our difference of our samples, right? So x1 bar minus x2 bar minus, and again, when we get into a test, we're going to assume no difference, and so the difference would be 0 over, and then that's where your standard error calculation comes from, which is your square root of S sub x1 bar squared over the first sample size plus S sub x bar 2 squared over your second sample size. A little bit rough to see there, but anyway, you get the picture. All right. Of course, since we're in a t distribution, those t values depend on degrees of freedom. So how do you calculate degrees of freedom? Well, how did we do it before? Well, degrees of freedom before was always one less sample size. There's a problem here. There's two samples. So which one do you use? Well, without technology, okay, we use the smaller sample size. Okay? Smaller sample size leads to a more conservative approach. Okay? If you look in your table B, as your degrees of freedom get smaller and smaller and smaller, your t values, your critical values, become bigger and bigger and bigger, creating a bigger margin of error for your intervals. And so it's a little bit more conservative that way. We want to make sure we're capturing, so to be more conservative, we have to make our interval bigger. Without technology, we're going to use the smaller sample size. With technology, it does a crazy formula. Feel free to go look at that crazy formula. That crazy formula is in your book, and the page escapes me right now. But if you're reading in your chapter, you'll come to it. If you're curious, ask, and I'll show it to you. But other than that, when you actually do your interval or significance test, it will tell you what the degrees of freedom is through technology. Okay? But without technology, we're going to use a smaller sample size, take one, I guess we ought to say one less the smaller sample size. So we put that in here. And then we'll use that for our degrees of freedom. Okay? Oops, wrong button. All right, so the formula for a two-sample t interval. And again, the general formula for confidence intervals in your formula packet, and it always says we need a statistic plus or minus some critical value times the standard error. I think it says standard deviation of the statistic in the formula packet, but we know standard error. Okay? So statistic. What is our statistic? Well, we're going to combine two of them. So we're just going to take x1 bar minus x2 bar, plus or minus your critical value is this t star, and then we're going to multiply it by the standard error. Okay? Remember that t times standard error is simply your margin of error. So if you ever want to talk about margin of error, this is it. Okay? And that becomes your formula for a two-sample t interval. Of course, these would be in parentheses. Okay? Now, of course, there are conditions that have to be met. We discussed them a little bit at the top of the video. Okay? But for our conditions, they're basically the same as for the one-sample test for a mean or interval for a mean, except that two things. One, we got to check both groups. And the other is that we're talking about means, we've got to make sure that our groups are also independent. So that's a little bit new. Okay? Not only do we want independence within our groups, but our two separate groups need to be independent as well. Okay? All right. Let's take a look at an example. Next is an example in your notes. Do plastic bags from Target or plastic bags from Walmart hold more weight? A group of AP Stat students decided to investigate by filling a random sample of 5 bags from each store with common grocery items until the bags ripped. Then they weighed the contents of items in each bag to determine its capacity. Here are their results in grams, right? So for the 5 bags from Target, the first bag took this much before it ripped, and the second bag this much, so on and so forth. And from Walmart, you can see the results of the weight in grams that was required before the bag ripped. So part A, construct and interpret a 99% confidence interval for the difference in mean capacity of plastic grocery bags from Target and Walmart. Well, it certainly looks like, just from the raw data, that the Target bags require more weight before they break, so maybe a little bit stronger. But we want to construct an interval to try to get an estimate for exactly how much more weight they'll carry, right? And so in terms of our state plan, do conclude. Here's what we want to do. We want to estimate. When we're doing an interval, we want to estimate. When we're performing a test, we're trying to test something. So make sure your language there is correct as well. But anyway, we want to estimate mean T minus mean B, so mu T minus mu B, at a 99% confidence level. Remember, you have to report your confidence level, and you have to talk about what it is you're trying to estimate. And so we have to define mu sub T, and that's the mean capacity of plastic bags from Target in grams. In other words, how much weight in grams they'll hold before they rip. Mu sub B is the same, only from not whatever Bashas is. I'm assuming the author of the notes has some other store in mind. Anyway, we're talking about Walmart. Okay? All right, anyway, so we have to change some of these words. So that's what we're trying to do. Okay, plan. If the conditions are met, we're going to calculate a 2-sample T interval for mu sub T minus mu sub B. Okay, so let's go check our conditions. First things first. Okay, random. The students selected a random sample of bags from each store, so the random condition is met. You'd want to talk about that. Okay, normal. Since the sample sizes are small, we're going to have to graph them, right? They're not bigger than 30, so central limit theorem doesn't kick in, and we don't know if the population distributions are approximately normal, so we're going to have to graph the data and see if it's reasonable to assume that the population distributions are approximately normal. Okay? When we do that, we can do a parallel dot plot, right? A parallel dot plot is just a dot plot that has 2 levels to it. And I'm going to, again, mark out this Bashas and write in Walmart. Okay? And so you can sort of layer your dot plot here. And the first layer is for Target, the second one's for Walmart. You look at the sample data from each, and we don't see any skewness or really anything that might be considered an outlier. There's not much of a shape at all. So since there's no obvious skewness or outliers, it's safe to use our T procedure, so we're going to go ahead and do that. Okay? Now, as long as our independent condition is met. So watch the verbiage here. The samples were selected independently, right? You just grab 2 samples from each store, and it's reasonable to assume that there are more than 50 plastic grocery bags at each store. So it satisfies the 10% condition, and we talked about the fact that the samples were selected independent of each other. So the groups themselves were independent. We want to make sure we mention both of those. Okay? All right. Well, our conditions are met, so we're ready to go ahead and do our interval. Okay, we need our statistics from our samples, right? So from our 5 weights in grams, we could type those into our calculator into a list, and then find the mean standard deviation for each, and you see those listed here. I won't waste your time doing that. Those have already been calculated, and they're right here. Okay? Now, conservative approach, degrees of freedom. Well, both samples are of size 5, so your degrees of freedom here are going to be 4. We're going to use that to find our critical value for a 99% confidence level. Now, this is the part where you're going to want to pull out your formula packet, go to table B, look across the bottom and look for a 99% confidence level, and then slide your way up until you get degrees of freedom of 4 and find that your T is 4.604. Okay? Any time you do a confidence interval where your degrees of freedom is 4, you're going to get a T of 4.604. Okay? So we have everything we need. We have our X bars, we have our standard deviations to put into our standard error. So we're ready to go ahead and do our confidence interval. Okay? And so that should look like, okay, and I'll label these here. We're going to do XT bar minus XB bar. Probably would make more sense if that were W, but anyway. This is our T star. And here we've got our S sub T, and this is our S sub B. Okay? You see the numbers plugged in, and then it just becomes an arithmetic issue. If you want to use your calculator to multiply anything out, you can. Or you're going to use, you can use your calculator to do a 2-sample T interval. Okay? And so we have our interval here. It's going to be 3,592 plus or minus, and again, this is our margin of error. Okay? Which gets us to an actual interval of negative 1380 to 8564. So think about what that means, right? The difference in the weights that are required to rip a bag from Target and Walmart, right? The difference could be negative 1380. Remember, negative would suggest that, where do we see it? That if it's negative, that mu sub b is bigger. So then it required more weight for a Walmart bag to rip, negative 1380. 8564 positive suggests that Target bag was stronger and took more weight to rip. So plausible values might suggest either to be true, okay? And then, of course, we want to conclude this. Now, when you do technology, okay, it's very interesting to see what happens. When you use technology, your degrees of freedom changes 7.5 instead of 5. And this is that crazy formula that I promised I'll show you if you really want to see it, if you haven't seen it in the book yet, okay? Well, that changes your confidence interval, okay? So it's incredibly important that you list your degrees of freedom now more than ever. That's why I had you do it before, so that you're in the habit of doing it and you do it now. So list your degrees of freedom, and then that will should line up with your confidence interval. If you're using the degrees of freedom of 7.5, this is going to be your interval. If you're using the degrees of freedom of 4, this it gets you this interval. Okay, and notice how much bigger this interval is than this one. This is why this is the more conservative approach, because it gives you a bigger interval to capture more values. Okay. But the calculator gives you a smaller interval with the same confidence level, right? Which is kind of important. Now, our conclusion. We are 99% confident that the interval from negative 1380 to 8564, if you're going to use the conservative approach, you could definitely use negative 101 to 7285 as well. But we are 99% confident that the interval from negative 1380 to 8564 grams captures the true difference in the mean capacity of plastic grocery bags from Target and from, again, this should be Walmart. Okay? Now, question B. Go back to that real quick. Question B, does your interval provide convincing evidence that there's a difference in the mean capacity between the two stores? Okay? Well, we just talked about it, right? I mean, the confidence interval suggests that Walmart bags are stronger on one end and then Target bags are stronger on the other. So it doesn't really provide conclusive evidence that one is stronger than the other. So part B, since the interval includes 0, which is another reason, right? Since negative on one side, positive on the other means 0's in there somewhere, then it's plausible that there's no difference in the two means. Thus, we do not have convincing evidence that there's a difference in mean capacity. However, if we increase the sample size, we would likely find a convincing difference, since it seems pretty clear that target bags have a bigger capacity. Now, what did that last sentence come from? Okay? Don't know that it's pretty clear that target bags have a bigger capacity. Okay? The data suggests it. Okay? But I think this last sentence gets you into a little bit of trouble. I don't think anything's pretty clear. Not when your confidence interval contains 0. Now, maybe a bigger sample size will provide that evidence, but we have to be a little bit careful about how we talk about that. Okay? So, you know what? For me and my taste, I think we should leave this out. If you haven't written this down yet, then don't. Okay? I don't think that needs to be in there. All right, anyway, there's your confidence interval. There's what it tells you. The same thing it's always told you, and we can use it the same way we've used intervals in the past. Okay? We'll stop there for now. We'll pick up significance tests in the next set of notes. Guys, enjoy your night, and we'll work on homework in the next class period.